Well,
it's certainly
it's a tool.
they're certainly both better than
Yeah.
I mean, at the end of the day, you're just gonna digital periods anyway, and you do.
I guess what
It's not like I need to have the very best 10 euros per stick of chalk, or anything. But it makes a difference.
Giotto is good as well. Just saying.
Oh, it's another type.
It's the Italian Giotto. They use it at Imperial. They used to use it there. Giotto is not bad. There are some French ones that people use as well. But as long as it's not expensive and you can use it correctly. Because now I cannot do it sometimes.
Yeah, I don't know what I need. Maybe I have some better technique, but yeah, sort of try pushing. Maybe I'm pushing too hard.
We might see each other next time. What was your name?
Yeah, maybe I need to push less hard. I think I'm sort of trying to make it work, so I'm really going for it. Does the camera follow you when I go over here? Is that what
it should be?
it should do.
Are you coming? Okay, so you can resume with the second lecture.
Okay, thanks for coming back. I wanted to application. Oh yeah. So Wojciech suggested that I write down. So I'm thinking about pi 0 of homeo x with a plus or without. So what I mean by this is, of course, I said this in words, but so I want to think about the connected components, and two homeomorphisms are in the same connected component if and only if they're connected by a path of homeomorphisms, and that's another word for an isotopy. So that's the same as then maybe orientation preserving if the plus is there. Homeomorphisms up to isotopy. So an isotopy would be a path f sub t from x to x. So t is in 0, 1. So for each t, there is a homomorphism, and these homomorphisms vary continuously as with time. And then f, this is said to be an isotopy from f0 to f1. And alright, this is a topological isotopy sometimes. So the shorthand for all of this is to call it this. Sometimes you might see in the literature, you might see people call it mod x or gamma x or the mapping class group of x, something like that. People have different notations. I guess this is my favourite one, so I'm doing that. Okay, so the next application I wanted to mention was just to, I mean, I'm not going to do all of this in detail, but let's think about some 2 knots. So a knot is a circle, a one-dimensional submanifold of S4, homeomorphic to the circle. A 2 knot is a 2-dimensional submanifold of S4, homeomorphic to to the two-sphere. So the images of these things, I guess technically, I want to talk about the images are two knots. And let's suppose that pi1 of the complement, so that's what we usually call the knot group, is infinite cyclic. So it's got the same knot group as the unknot. In fact, we may as well assume that F1 is the unknot. So maybe F1. Let's just say F1 is F1 of S2 is the completely standard embedding of S2. And I can take S2 and embed it as the equator of S3, and then embed S3 as the equator of S4, and I get a standard embedding of. So this is the I suppose this is the two knot. Then. Right, so I want to understand these things. So if I take the normal bundle of such an embedding, or a tube, well, I'm going to take a tube in a neighbourhood, in fact. So it's in general it's a disk bundle over the two-sphere, but actually in this case it's always a trivial disk bundle. That's true for both of them. So there exists. A homomorphism from the normal bundle of F0 of S2 to the normal bundle of F1 of S2. So I've got these two knots sitting in 4 space, and then they're thickened. And just thinking about the abstract neighborhoods, I can send one neighborhood to the other. I mean, they're both identified with S2 cross D2, and I can do this in such a way that if I take the zero section, they're both identified with S2, and that I get a bundle map. In fact, they're both S2 cross D2s, and they both have a projection to S2. And so in particular, this sends, F0 of S2 to F1 of S2. And then the reason I'm saying all this is because then I want to quote a theorem. So I'm only going to tell you about a very small part of this application. This is a non-trivial, very non-trivial theorem, but this has to do more with the question of classifying form manifolds, proving that two form manifolds are homomorphic to each other. So now that I've got a homomorphism of the neighbourhoods, one neighbourhood to the other. Now I can just remove the interior and think of that as a homomorphism from the boundary to the boundary, and then I want to know, does this extend to a homomorphism of the complement of one knot to the complement of the other knot? And the answer is yes. So G can be extended to some homomorphism G hat from the 4 sphere to itself. So that will have the property, that's why I tried to go through this before, it has the property that it sends one sphere to the other. So they're what we would call equivalent knots. And again, this is kind of, there's a lot, if I were to tell you about the proof of this, it would take a while, but maybe just, we can accept for now that, I suppose one is good at showing whether two form manifolds are homomorphic to each other. Then what do you get? Well, one thing you get is you can prove that by this mechanism, by considering the exteriors of the knots, so I cut both the knots out, and then I have a homomorphism on the boundary of them, and then I already have this homomorphism on the neighbourhood, and then I have the exterior, and I want to kind of then extend that to a homeomorphism from the exterior of this one to the exterior of this one. Exterior means S minus an open tubular neighbourhood of them. So this is what I call exterior. I mean, complement is just where you actually remove the thing, and exterior is where you remove an open tubular neighbourhood. So this way you get a compact manifold. So I like that better. Yeah, so that's good, but now what's the point? The point is just that, because we saw that, this is, in particular, this is orientation preserving because, I started off with my G, the original G was, I start off with one of those that respects the orientation of S4, then when I extend it, it still will. So I get an orientation preserving thing. But then we saw in our very first example that this is just, there's just a single map. It contains the isotopy class of the identity, and that's it. So therefore, G hat is topologically isotopic to the identity, and this isotopy tells you that our two knots are ambiently isotopic. Because I start with this homeomorphism that sends one to the other, and then this homeomorphism gets deformed to the identity. And so on the one hand, I have my F0 of S2. To begin with, F0 of S2 gets sent to this one, and then I deform it by looking at its image. So suppose I have this G sub T from S4 to S4, where G of 0 equals G hat, and G1 equals the identity. Then if I take G sub T of S2, that's going to have the property that G sub 0 of S2 is G hat of S2, which is F1 of S2, so that's one of my knots, whereas G1 of S2 is the identity, GT of F0 here. Let me get this right. That's better. Is the identity of F0 of S2, which is, of course, just F0, once I get out of the way. So, yeah, I get this one parameter family, and at the beginning, it gives me the F1 of S2, one of the knots, and at the other end, it gives me the other knot. So they're isotopy. So, no, yeah.
Where do you use the assumption that the pi 1 of the complement is Z? It is in the Friedman-Quinn theorem? Or?
Yes, yeah, yes, it is. Yeah, this. So that's that we don't know that for all two knots. I mean, it's just right.
Yeah,
I mean,
sure.
yes, yeah. So here they particularly proved this for the knots with Z. Yeah, okay. Not group Z. Yeah. There are extensions to this theorem to other cases. That's particularly proven in their paper. So I was trying to make the point that once you have a theorem like this, if you know about the mapping class group, you can improve a statement about equivalence to a statement about ambient isotopy. So it tells us that every two knot that satisfies this property is unknotted, is isotopic to the standard one. So you only need to, if you can compute the fundamental group, then you learn that your knot is topologically trivial, and it's a famous open question whether every smooth two knot with knot group Z is smoothly isotopic to the identity. We don't know that, but it is this. Mapping class group won't help you. I mean, if the two knot is smoothly equivalent to the unknot, then it's also smoothly isotopic. So there's somehow not a it's a question about knotted surfaces as opposed to a question about smooth mapping class groups. Okay, so I've done introduction, examples, applications. Now I want to move on to starting to talk about how we actually prove such a statement. So now would be a good time for any further questions about the general. Although we did have a bunch of questions in the break, so thanks for those. Okay. Get rid of that too. Is this now just about legible? I think I'm getting better with this chalk, so. So I need to tell you about pseudo-isotopy. So, how do we prove So how to prove that? And yeah, the key concept is pseudo-isotopy. So this is a way of breaking up the problem into two steps, and seems to be sort of a very key notion for being able to attack this problem. And the methods, as we'll see, the methods for thinking about the two steps are just very different. So what happens? Yeah, so I'm going to use cat is for manifold category. So cat is either top for topological category or diff for the smooth category. I just wanted to be able to make one definition all at once. And X4 is going to be a compact four manifold. Then so a cat pseudo-isotopy, and I'm often going to write pseudo-isotopy as PI, probably PI for pseudo-isotopy, because it gets annoying to keep writing it out. Of X is a cat isomorphism just goes over the board. In other words, a cat isomorphism means either a homeomorphism or a diffeomorphism, depending on which category you're in. I could have talked about piecewise linear category too, but I decided not to. PL would look a bit too similar to PI. Wouldn't be good. So it's usually going to be capital F, and it's an isomorphism from X cross I to X cross I, such that it has to be when I restrict to, this is a funny symbol, I'll say what this is in a minute, that thing, I get the identity. So if this is X cross 0, and this is X cross the interval, and this is X cross 1, then that funny symbol means all of that part there, the thing it's supposed to supposed to indicate that. So it means that x cross 0, formally, this means x cross 0 union the boundary. I'm temporarily allowing boundary. I mean, usually we're going to be thinking of the closed case, but I just want to give the definition of pseudoisotopy without restricting, because, well, we might want to use it, and it just seems silly to only give half of the definition. That's fine. So I require that my homomorphism or diffeomorphism is the identity. It's completely fixed on all of this part. It's just it's allowed to move the middle, and then in this we say if I have such a thing, I consider f restricted to x cross 1. So I have some homomorphism of this to itself. I restrict it to this end. And we say that thing is pseudo-isotopic to the identity. I might write I'll probably shorten that to P, so pseudo. PI can mean pseudoisotopy, or sometimes it can mean pseudoisotopic, depending on the grammatically correct usage. So as a notion, it's not too difficult. I'll try and argue that it's sort of a natural definition to make. I mean, the main reason it's a good definition to make is because I'm gonna be able to prove that a homomorphism is pseudoisotopic to the identity, and in fact, I'll also be able to prove the same thing smoothly. And then I'm also going to be able to prove that something that's pseudoisotopic to the identity is isotopic to the identity. So, see remark. So if I have a cat isomorphism, then, or lowercase f, then isotopic to the identity this is kind of an exercise, so, I mean, an exercise that I'm going to tell you the answer to, but. So if it's isotopic to the identity, then it's also pseudoisotopic to the identity. And pseudoisotopic to the identity implies homotopic to the identity. And of course, homotopic to the identity implies f star equals the identity from that it acts. That's supposed to be a k. Okay. So, of course, if you're homotopic to the identity, then you act as identity on homology. So that's 3. So I claim that it sort of fits naturally in this hierarchy of things that you might want to know about homomorphisms, so we will see for if X is closed. Sure. X is closed and one connected, then all of these are all of these are in fact if and only ifs. But that's sort of what I want to show is that these, well, yes, these are So, but this direction, this is the quote easy direction. So, so how do we see this? If I have f sub t from x to x, that's a homeomorphism for all t in 0, 1, then I can, that's a squiggly arrow, that means gives rise to, that gives rise to an f from x cross I to x cross I, and I'm just going to send x comma t goes to f sub t of x comma t. So it's very easy to then construct a pseudo-isotopy. But this is a very nice type of pseudo-isotopy, namely that it's level preserving. So if I have a pseudo-isotopy that's level preserving, so it takes each so I take each thing of the form x cross t. So if sort of f of x cross t equals x cross t, this image, if that then f is level preserving, and this is for all t in 0, 1, it has to be true for t equals 0 and 1, but if it's true for all t, then this is level preserving, and f is isotopic to the identity. So this is another thing. If I have a pseudo-isotopy and I can isotope it to be level preserving, well then in fact I can go even further, and actually if it's level preserving, this actually implies that because f is the identity all around here, if it's an isotopy, I can actually isotope the whole thing to the identity. So this actually implies that the entire capital F is isotopic to the identity of x cross I. So if you could have one, if you have a level preserving pseudo-isotopy, then you get an isotopy. And what I'm saying here is if you have an isotopy, then you get a level preserving pseudo-isotopy. So you certainly get a pseudo-isotopy, it's just a particularly nice type. And then, right, just think through the next one. If I start with a pseudo-isotopy, f from x cross I to x cross I, then I can just project to the first coordinate. So here's my pseudo-isotopy, and then if I compose with a projection, that gives a homotopy. So this is a homotopy from lowercase f to the identity. So yeah, sorry, sorry, I don't know if I said that properly. My notation is that I take this capital F, that's a map from x cross I to x cross I, and then lowercase f is the restriction to x cross 1. So here when I wrote the lowercase f for the thing that's pseudo-isotopic to the identity, and then I want to think about when I restrict it to the, f sub t is a family, and then if I have a pseudo-isotopy and I restrict to f cross 1, then I call that lowercase f. So lowercase f is supposed to be homeomorphisms, and uppercase f is supposed to be pseudo-isotopies. So this was supposed to convince you that it's not too difficult to see these implications. An isotopy gives you a pseudo-isotopy, and a pseudo-isotopy gives you a homotopy. This is somewhere in between. Okay? So this is going to be an important notion, pseudo-isotopies. Maybe I'll just talk about some more generalities. So if I have F and G, also cat isomorphisms, or we can just think of these as being homomorphisms now. So these are cat pseudo-isotopic if but I mean this is what we're defining, and I want to say if G inverse F is pseudo-isotopic to the identity. So there's not too much going on here. I just want to think about if I have a pseudo-isotopy, so that's something like this, and I have a pseudo-isotopy to the identity between these two things, then I can post-compose with G and get something. Just take G, compose F, and then that's going to interpolate between F and G. So F and G are then going to be pseudo-isotopic. So there's no particular reason. I mean, I just wanted to address the fact that when we speak of a pseudo-isotopy, I define it to be the identity on one end and something on the other end. But because we have a group, it's enough to just think about, if I want to decide whether two things are the same, it's enough to think about, is one thing equivalent to the identity? That's the only point I'm making. So I'll say that two things are pseudo-isotopic if they're related in this way. So you could think of the pseudo-isotopic, the formal definition was this, so that I could relate it to the previous definition. But you could think of it as just being, there is some homomorphism of X cross I to itself that restricts on one end to one of your homomorphisms and on the other end to the other one. But somehow so that's what I mean by saying two are pseudo-isotopic, but usually we'll just think about one thing and the identity on the other end, and that will be sufficient. But this definition lets me make another definition. So I can compare all these objects. So this is going to be pi 0 tilde, and you shouldn't think of this as having, like, this might be, you may not like this notation. I apologise if you don't, but I'm not going to change it, so I don't apologise that much. This is a composite symbol, so this is not like take homeo x, apply. I mean, it's not really like there's not a thing called pi 0 tilde. It's just what this really is. In fact, is pi 0 of. I mean, there is actually a space called this, the block homomorphism space, that I could consider, and then I'm taking pi 0 of that. But it just, that big tilde doesn't look so nice when you typeset it. It looks a lot nicer to put the tilde just on the pi, so that's what we do. So just think of this as this is a symbol that means this. Well, what does it mean? It means homeomorphisms again, so it's exactly the same objects. So homeomorphisms, or orientation preserving homeomorphisms of X up to pseudoisotopy. So up to this equivalence relation, the equivalence relation generated by this thing. And then once I've defined that, so that's a perfectly good thing. I can think of homeomorphisms up to pseudoisotopy, and then we can factor. So we had our original thing that we wanted to understand, and now I can take the pi0 homeo plus of X, so mapping class group of X, and then I give these maps names. So I just take the same objects, but I consider them instead up to pseudoisotopy. So I can take this map, and then I could do, before I had this thing where I said, okay, if I've got an isotopy, it gives me a pseudoisotopy, and if I've got a pseudoisotopy, it gives me a homotopy. So then I could also take the space of homotopy self-equivalences, so H stands for homotopy. So this is homotopy automorphisms of X that are orientation preserving. So there's some intermediate thing. So this means homotopy self-equivalences. So it maps from X to itself with a homotopy equivalent up to homotopy. So homotopy classes of homotopy self-equivalent. The pi0 now means up to homotopy in this group. It's not an isotopy anymore. So this means the homotopy classes. Homotopy classes of homotopy self-equivalences. And then I can just from there I can map to H2 of X comma lambda X. And so that one I called phi2, and that one phi3. So the original map in the statement of the main theorem that I want to discuss is goes from here all the way to here, and so it's an isomorphism, and we will show that phi1 and so this map's an isomorphism, and phi3 compose phi2 are isomorphisms. So the only problem is this one is slightly different because there are more homotopy self-equivalences of a manifold than there are homeomorphisms. So there's some extra stuff in here. You can take your 4 manifold and you can pinch off an S4, and then you can map the S4 onto an S2 in your manifold using the non-trivial element of pi4 of S2, and that will give you that gives some nice homotopy self-equivalences that aren't homeomorphisms. So this one is sort of slightly bigger. This one sort of maps into here, and then some things die again when you go here. I just wanted to put this in there so that you can sort of see all the different ways, all the different objects one could look at. But what we're actually we're going to kind of skip this one out in what we do, and we're just going to show that this one's an isomorphism and that this long map here is an isomorphism. So that's sort of the goal. And if you want to see about, I'll just write down the key names for this one. There's a brilliant paper by Cochrane and Harberger that analysed this group very nicely. So if you want to know about that, there's a paper there to look up. Yeah, so that's pseudoisotopy. Okay. So how am I doing? 5 minutes, right? Okay. Any questions about pseudoisotopies? Now I want to start explaining. The next thing is I want to start explaining why this is injective. Oh yeah. So I was trying to pause. It's kind of a bunch of definitions, but I do want the definitions to be clear, so please Please tell me if they're not. Okay. Now you see the first sort of lie is that I'm just going to by a lie I mean I said I was going to prove it, but actually I'm just going to state half of it. So if X is closed and simply connected, then Friedman proved part of his famous theorem about classifying the classification of simply connected four manifolds up to homomorphism. If you look at that, and the really refined version of that isn't just, it's something, so what it says, if I have two four manifolds, and if they have isometric intersection forms, and they have the same Kirby-Siegmann invariant, that's an extra Z mod 2 invariant, then they're homomorphic. So that's Friedman's classification theorem about closed simply connected four manifolds. Isometric intersection forms plus same Kirby-Siegmann implies homomorphic. But it actually says something slightly better. When you actually go through the proof, which we're not going to do, because it's just, there's two parts. You have to prove surjectivity and you have to prove injectivity. And I want to talk about the injectivity part, and this is the surjectivity part. What it says, what does surjectivity mean? It means given an isometry of the intersection form, there exists an orientation-preserving homomorphism of X, inducing the given isometry on the intersection pair X. So, I mean, the way the classification is usually stated is if there exists an isometry, there exists a homomorphism. But it's actually much more refined than that. For any given isometry, there exists a homomorphism inducing it. So that's the same as saying that this thing is surjective. Is surjective. And if you want to know about the proof of this, I recommend a really nice book. Every time you buy a copy, I get about 50p. So keep those royalty checks coming. Get myself a Coke once every 3 months. But I mean, I sort of decided not to focus on this part because. Well, I wanted to give talks about the other part, so that's what I'm doing. So we're going to focus on the injectivity, and that will give us plenty to do. So the first thing is, which I will do. I mean, there's not going to be much time to say much about it this time, but I want to show that this map is injective. So this was this phi 3 composed phi 2. Is injective, i.e. if I have some homomorphism F, then if its induced map is the identity on H2 of X, then F is pseudo-isotopic to the identity. So this is going to be the goal for next time. Well, I mean, I'll start it. I'll start saying something about it now, so we know where we're going. So the key idea is to consider the mapping torus. So I draw you a wonderful artist's impression of the mapping torus by drawing a torus. So here I have X cross the interval. And here I have another version of X cross the interval. And remember, what I want to do is make a pseudo-isotopy. So I want to get a homomorphism from this one to this one. And what I do is I glue together here. This means I'm going to glue together here using the identity map, and here I'm going to glue using my given F. And well, glued by the identity map isn't really doing anything. So this is just the same as taking what's called TF as the mapping torus. So this is the same as taking X cross, I mean, maybe I should call it, since I have 2 copies of X cross I, maybe I should call it 0, 2 now. And then I'm going to send X. X comma 2 is glued to f of X, comma 1. So I just glue with the, I take X across the interval and I glue using the...
Comma 1 or comma 0?
0, 0. Thanks, yeah. I confused myself by changing. I should have just used this. I don't like it. Let me... I'm just going to do it like this. This is what I wanted to write. So... It's all, I mean, it's all homomorphic either way. This to me is the standard definition of the mapping torus. I've sort of presented it here as 2 copies. I don't know which is... The 2 things are homomorphic, but the way I want you to think about it is like this. It's sort of 2 copies of the interval glued together at the top and bottom, one by the identity and one by f. Because what I want to do now is, so the aim is to find an H cobordism. So an H cobordism is in particular a cobordism. So this is a 5, this is a 4 manifold, so this is a 5 manifold, and I want to fill it in with a 6 manifold. So this is going to be a 6 manifold, and it's going to be a cobordism from X cross I to X cross I. I think of it as a cobordism from this one to this one. And I want it to be an H cobordism. So an H cobordism means that that inclusion map and that inclusion map, so there's 2 maps from X cross I into V are homotopy equivalences. How are we doing for the... Oh, so should stop. Yeah, okay. I'm going to stop. I'm going to say one more thing, and so it finishes this idea, and then I'm going to stop. So that's what an H cobordism is. And so this is the aim, is to find one of these, and then once we have this, there's the H cobordism theorem. Actually, in this dimension, this is true smoothly. So everything that we're doing here, we could have also done with diff. I could have said diffio class of X, and it was also true, and it would have worked just fine. So there's really no difference between the smooth and topological categories in this part. So what does the H cobordism theorem say? It says that if I have an H cobordism simply connected, then it's a product. It's a trivial cobordism. So that says that this. So there exists a. Well, this implies. So the H cobordism theorem is due to Smale, and the topological version, Kirby and Zieberman. They adapted Smale's proof. This is a trivial cobordism, so that's X cross I from X cross I to X cross I. And I wanted to give this a name. So this is just called G. And then if I now just take G restricted to X cross I cross 1. So I've got X cross I here, and if I now just, so I've also got another thing like this, which is X cross I, and then on this it's the identity. So this is something, and it's rel the identity on X cross I cross 0. So on this one it's the identity, but on this one it's something interesting, and this is a pseudoisotopy, and it's a pseudoisotopy from F to the identity. Okay, so I'll stop there. So that's what we're going to do next time.
Okay, so let's thank Mark. Any questions?
So what does all of this
notation mean? Like your V6, XI,
Oh,
yeah, all of them.
Okay, you should ask this during the lecture. So, the superscript is just a way of saying it's reminding you of the dimension of the manifold.
Yeah.
That's all. So I can delete that.
Yeah.
Just reminding you it's a six-dimensional
But it's like, that is the normal notation for kind of a coboardism from something to something.
Yeah, that's what this. Yeah, so I think this is the normal notation in my work, where you have. So my notation is, I say the coboardism is called that, and it's a coboardism from that to that.
Okay.
So in the topological field theory thing, that would be a morphism from this one to this one. And so I'm trying to write down the coboardism and then the names for the incoming and outgoing manifolds. And when these have boundary, the coboardism is just a product on the boundary. So the boundary is x cross 0 and x cross 1, and then I have a little product on the boundary. But I'm gluing with a very particular map on the top and a particular map on the bottom. So in this one I just have the standard thing, but this one I identify the boundaries with, well, this one in the standard way, but here I identify it using my map F. So I've got there's something missing in this notation, which is the way that the boundaries are identified. And that was very important for the whole thing. So the two boundaries are both copies of x cross I. They're a coboardism of manifolds with boundary is a coboardism where on the boundary you have a product, but you do have to sort of identify the boundaries in a nice way. So I take these, so this thing, the boundary of V equals TF. That's the way it has to be. So I'm looking.
There's something you could write down just so that I can
that one.
That and yeah, there's boundary thing.
There's a boundary thing. Yeah, I have to write that down. Yeah. So I mean, when I say find an H coboardism, I meant find an H coboardism in there. I coloured it in.
I don't understand what it is that you called in. You had some mapping torus.
I have this mapping torus. That's a 5 manifold.
Yeah.
And I just want to find a 6 manifold with boundary. So I want to find a null coboardism. So V is a null boardism for TF or TF. So it's just a 6 manifold whose boundary is the mapping torus. But it also has the property that this inclusion map and this inclusion map are homotopy equivalences. I want to find.
And this is this boundary thing.
That is a rel boundary H coboardism, a rel boundary boardism, or rel boundary H coboardism from x cross I to itself, relative to identity in F. So this is a rel boundary H coboardism. It's an H coboardism rel F disjoint in the identity on the boundary. Maybe that's what I should say. Yeah, sorry. I'll do this again at the beginning of the next time, because we're going to need to go from there. I just wanted to explain the philosophy. This is the way that you prove that you construct pseudo-isotopies, is you.
Okay, any further questions? Okay, so if not, let's thank Mark again. And tomorrow, please remember that we meet at the Department of Mathematics, so in room 21A. So if you've been at the conference on the previous week, so you should know where the room is, because this is the same room. And if not, there should be a map on the website, so that you can be able to find. Hopefully. 21A. 21A. I have this like a thing. Is this what this?
Yeah.
For this?